Hey, a few things before I forget. So the exam, of course, is next class, Friday. 1 o'clock, bring a pencil. The exam will try to cover material since about flashlights until through today, which will be microwave ovens. That's as far as I'm going to go. So if you look at old exams and you find questions about sunlight things, refraction, Rayleigh scattering, a few things like that, those won't be on this exam. So you could skip over those in taking old exams. The other thing about old exams is this class, for the many years I've been teaching it, I rearrange stuff from time to time when technology changes, for one thing, and a whole topic disappears from my collection. I used to teach about telephones, because they used to be the old, the things you see in the old movies, right, with the dial and all that stuff, and it's all gone. So I rearrange, and the consequence is that some stuff just in the old exams is no longer, we don't do it, or it's not, we don't do it yet. So things like, if you see on the old exams discussions of light-emitting diodes, or diodes in general, or MOSFETs, which are a type of transistor, they're in our future. We haven't done them yet. I used to do them by now, but I changed. So be aware and taking the old exams of some questions that are just out of the blue. Where did that come from? You're not responsible for that. Any other questions about exam stuff? Exactly. N-type semiconductor stuff? No, that's in our future too. We'll get that. That's electronics. I used to teach electronics before radio waves. Now I teach it essentially after. Toward the end of the course. Anything else like this? Okay. My goal for today is to talk a little bit more about the radio wave, how radio waves transmit information, then to talk about microwave ovens, which is pretty short, I hope, mostly fun and games. It's not a lot of new physics. And then lastly, to revisit transformers a little bit, because I've talked to a lot of people in the past couple of days. I've clearly left a lot of things unclear. All right? So issue one, and I can do this without slides, or maybe you want to see images. Just I'll pull up. A constant radio wave is a radio wave, but doesn't transmit any information. If you want to transmit information like fluctuations in air pressure that are sound, you have to do something to the radio wave that symbolizes or represents those fluctuations in air pressure. So the radio wave isn't carrying sound literally, it's representing the sound. It's sending the information that is in the sound so that a distant receiver can reproduce the sound. Is that okay? The idea that you're representing the information. So the two classic techniques for representing sound are AM and FM. AM short for amplitude modulation. So the slide title here is redundant. It's amplitude modulation. Oh well, that's the way it is. Amplitude modulation is the way you represent sound and the pressure fluctuations that are sound as variations in the amplitude of the wave, how strong its electric and magnetic fields are. You turn up the electric and magnetic fields to represent high pressure. You turn them down to represent low pressure. Back and forth, back and forth. Is that okay? That technique can be used at any radio wave frequency, any radio wave wavelength. Frequency and wavelength are related to each other. Any questions about that idea, that the longer the wavelength is, the less crests go by every second, so the frequency gets lower. So as wavelength goes up, frequency goes down. Questions about that idea? Okay. You can use AM modulation anywhere you like in the radio spectrum. It is, by convention, used in a special patch of frequencies that I guess are called the AM band, that are between about 500,000 cycles per second and 1.6 million cycles per second. That's the standard classic AM range, and so it goes. All right? The other technique that's commonly used is frequency modulation. Again, FM. It's redundant too. So FM is the signaling technique. Instead of turning on and off, up and down the intensity of the wave, the strength of the wave, they take the frequency, and the frequency that the radio station has is the one that they tell you about. I don't know, 101 on your FM dial or something. What's 101? It's 101 million cycles per second. That's the center frequency, the official frequency that they're allocated, but they're allowed to migrate a little bit to higher and lower frequency. And for various reasons, yeah. So they can go to 101.0. How much do they allocate? Maybe a 0 or 2 and then another 1. They're allowed to dither around in frequency a little bit. And this is why the radio stations have to be separated from one another by a certain significant frequency distinction, because they don't transmit purely at one frequency. They dither around it. And for reasons having to do with the nature of the mathematics of playing with a pure frequency, they necessarily end up using a bandwidth, a range of frequencies. They wipe it out, they consume it, they occupy it. And so the 101 on your FM dial occupies more than just literally 101.0000000. It's got a range, a bandwidth. That's a whole story that I won't do. Anyhow, they can then represent pressure fluctuations up and down in pressure with very subtle frequency fluctuations. They go a little higher than their official center frequency. They go a little lower than their official center frequency, back and forth, and thereby represent sound. Is that okay? And we actually have a system for transmitting FM. And you can get these things. You've seen up here our totally homebrew versions. This is a commercial one. This device takes in an audio signal, which could conceivably be me talking into a microphone. When I do that, my voice goes to the microphone. The microphone, I'm doing it, of course, right? I've got a microphone in front of me. It's representing the pressure fluctuations that are my voice as current fluctuations in a wire. And if this then connects to that transmitter, the transmitter then represents those pressure fluctuations that are represented as current fluctuations as frequency fluctuations in the transmission of that coming out of that antenna there. And this receiver over here receives the wave coming in and reproduces the sound. I can't unplug the, yeah. Okay, you get the idea. No, don't start. Okay. So there's no physical connection between these two systems. This over here is sending a current in that's representing sound that was recorded somewhere way back. It's then being, a radio wave is being transmitted, and the frequency is being gently, very subtly dithered around about the center frequency. This guy over here is seeing that radio wave. That radio wave being transmitted over there by a relatively short antenna. That's an undersized antenna, but the systems are so sophisticated these days they can make do with it. Charge is being driven up and down on this antenna. That's transmitting a vertically polarized electromagnetic wave. I know that because it's a simple vertical antenna. It's shoving charge up and down this little black guy here, right? Charge going up and down that guy. That creates a vertical electric field, horizontal magnetic field. They go whizzing across over here. They begin to shove charge up and down this antenna, which is a more appropriate length for really receiving FM. The charge gets driven up and down that by the passing electromagnetic vertical electric field, and this guy then sees, oh, there's a radio wave, and it's centered on my official designated frequency, but it's dithering a little bit. It's going a little high, a little low. I'll move the speaker in response. Every time it goes to a little high frequency, I'll move the speaker towards the listener to compress the air. Every time it goes to low frequency, I'll pull the speaker away to rarefy the air and back and forth. It recreates the sound that way. Questions about that? We've gotten really out of the habit of questions. Okay, so you can transmit it. In the transmission, you might think that it's all the little electric and magnetic fields right around these wires here, but no, actually, they managed to send part of that electric and magnetic field off as this team structure, this electromagnetic wave structure that doesn't remain attached in any way to this transmitter. It goes off to the edge of the universe. So that transmission I just sent out, we received a little bit of it over here, and a little bit of its power was literally received by that radio receiver. But the other portion is now heading off. It has long since passed the moon. It hasn't yet gotten as far as the sun. The sun's about 8 light minutes away, something like that, 8 or 9. But it's going to head off. It'll leave the solar system in some number of hours, and it'll keep going. It will never, a good part of that transmission will never stop. The end of time. Okay? I could turn all the toys off. Off. Okay. So that's AM radio, FM radio, representing information. You can represent things other than sound. For example, you can represent images, and that's how television developed. You can represent just sheer data, and that's how you end up getting internet and whatever on your phones. They probably aren't using AM transmission. It's kind of passé. They're probably using variations on FM transmission, very sophisticated embellishments on the FM concept. In recent years, FM radio stations have started having digital. There's been digital FM and HD radio, and where one old-fashioned radio station now transmits several radio stations because they've managed to just start inserting data into the transmission along with sheer sound, simple sound. But it's all the same kind of idea. You're playing with the radio wave, subtly changing it in order to represent information. Generically, any old information. Sound was the original, and now we're off into the latest scores on the sports games. All right, any questions about radio waves, radio transmission, radio reception? Okay. All right. Next topic to pay attention to, and I'll keep it short, or try to, is microwave ovens. And the reason I can keep it short, I mean, I've got questions embedded in it that I'm not going to ask. Microwave ovens, it's the same story again. It's just a radio transmitter, except that the radio wave being transmitted has a much higher frequency, much higher frequency than the FM band, say, certainly than the AM band. The frequency gets pretty high, and as the frequency gets higher and higher of the wave, the wavelength gets shorter, right? And once the wavelength of the waves becomes shorter than about this, 1 meter, they stop talking about them as radio waves. They just change the name. They tend to be called then microwaves because they're less than 1 meter. I don't know, it's just a convention. So a microwave oven, it's just radio waves, except they're short wavelength, high frequency, short wavelength. Your cell phones communicate entirely with waves in this range, the microwave range. So your phones are little microwave radio sources. There's always this concern about cell phones destroying you in some manner or other. They don't transmit very much power. They don't cook you very effectively. The microwave oven, yeah, that bites. You do not want to be inside a microwave oven. But the microwaves transmitted by your phone are just minuscule in comparison. Wi-Fi, incidentally, at least the original Wi-Fi, not the 5 gigahertz Wi-Fi, the original Wi-Fi uses the same waves and the same wavelength and frequencies as microwave ovens. That's part of, they were unallocated, left for the microwave oven world, and they got double use. People use them for Wi-Fi as well. All right, so the story of microwave ovens is pretty short in the sense that it's the same thing, electromagnetic waves. they go whizzing around. They have a wavelength. The frequency is about 2.5 gigahertz, 2.5 billion cycles per second. And so the wavelength is something like 11 centimeters. These are numbers I used to have on the tip of my tongue, but I forget them after a while. So the wavelength is pretty short. The crests are very close together. They whiz by you, a lot of them per second, and therefore the frequency is quite high. So 2.5 gigahertz. The simplest antennas for 2.5 gigahertz, an 11 centimeter radio wave, is a half wave antenna. If you have both halves, you put the positive half goes up, the negative half goes down, and then they reverse back and forth. So an antenna that's about 5 centimeters-ish, 5.5 centimeters, would be really nice as a half wave antenna for these microwaves. But they don't use the whole half wavelength antenna. They use only the top half, and they put the rest, they put it on top of a conducting surface. So the transmitting antenna for the microwave oven, and it's there, it's real, it's in there, is about 2.5 centimeters long. It's a little guy. And let's see, this is east. I probably can show it to you. How do I do this? I have to remember the east. Yeah, you're now in this camera. Al has set up. You're looking inside the microwave oven, right? Al has set this up, and I'm going to mess with it immediately. I'll take you inside and see whether we can see the little transmitting antenna. Woo! I take life so seriously here. Okay. So now we are inside, and you see, there's a cover sitting here. You're looking at the right side of the box, and there's a cover there. That cover is some sort of ceramic-y type thing covering a little hole. We're going to go explore it. We're going to go find someone's treasure. It's like one of those reality shows where they open Capone's stolen loot, whatever. Inside here, oh, I have to go get a flashlight. We'll find out whether the vault has any money in it. Look at that. There's a little antenna. See the antenna, guys? That's it. That's the antenna. It's about as build. It's about 2 or 3 centimeters long. You can't tell that because, of course, this is a real close-up. But that little box is otherwise empty. Get your act together. All right, I'll stop. It's driving us all crazy. Okay, so there is really a transmitter inside this thing, and it's transmitting a wave with a quarter wave antenna, and that wave is super intense. It carries typically something like 700 watts of microwave power, a lot of power. Very strong electric and magnetic fields. Come on, let's get this together. Oh, stick it in the right spot. Good, got it. Okay, we're back in business. So, the microwave oven has a radio transmitter in it. It's not radio anymore because it's higher frequency. It's called microwave. That device was developed. It's called a magnetron. It was developed during World War II as a transmitter for radar. It made radar possible, which was a huge advance. Certainly one of these things that was fundamentally changed the way the war operated. The fact that you could send out these very strong electromagnetic waves, bounce them off things. They do bounce off metal, particularly conducting surfaces, and you can see the reflection, so you can detect things off in the distance. All right, so there's a transmitter inside that box. The box, incidentally, what I call a cooking chamber, is all metal except for the front door. It's all metal, and what happens when an electromagnetic wave hits a metal surface? Well, because it has electric fields in it, the microwave does, or the radio wave in general, it pushes charge around. That's what electric fields do. They push charge around, and they cause a essentially perfect reflection of the electromagnetic wave. So when an electromagnetic wave encounters a conducting surface, a surface that can really respond beautifully to the electric field in that wave, the wave reflects. And it reflects. This is how mirrors work. If you ever wonder why it is when you look in a mirror, you see yourself, normal mirrors, the ones that you encounter, are metal mirrors. They have typically a plate of glass that you look through, but what you're seeing isn't the plate of glass by and large, although there's a little bit of a reflection even from glass, as you know, and we'll talk about after the exam. The main reflection you see is caused by electromagnetic waves pushing charge around in that metal layer. It's not, these days it's aluminum. Historically it was silver, and it was a little bit fragile, which is why you see antique mirrors that have sort of come apart in various ways. Modern mirrors, aluminum sort of is forever. You're seeing the reflection caused by the conductivity, the electrical conductivity of that surface, and therefore its ability to reflect the electromagnetic wave almost perfectly. So that box in the microwave, similarly, is metal, 5 sides, top, bottom, back. 5 sides metal. And it reflects the microwaves almost perfectly and keeps them in the box. Well, that leaves the front surface. The front surface is a little complicated. It's glass because they want you to be able to see. You watch the stuff cook. But it's not entirely glass. It's typically got a metal screen with lots of little holes, but it's mostly, it's a mixture of metal. You can see it here. Try this again. The resolution doesn't do it for you. But you all know, you look in a microwave oven, you're not looking just solid glass, just totally transparent glass. You're looking through a screen. Why a screen? The screen has holes in it, but otherwise it's metal. And it turns out that electromagnetic waves cannot detect structure that is significantly smaller than their own wavelength. A wave that has a wavelength that's big compared to one of these holes means its frequency is low enough that electric charge has time to go around the hole and make up for any failure of that hole to actually conduct electricity. So the wave is just, its variations are too slow to have that hole be a problem. It reflects perfectly off the surface anyway, hole or no hole. So the holes are deliberately made much smaller than the wavelength of the microwave. The microwave, again, has a wavelength like this. The holes, as you know, are little guys. And because they're little, the microwave essentially cannot see the holes. It reflects perfectly. This is a general observation about electromagnetic waves. They can't detect and respond to structure that's significantly smaller than their own wavelength. And this is why light microscopes, and those of you who've looked at things under light microscopes, you can see stuff down to about pushing the wavelength of light. The wavelength of light's pretty small. It's less than a millionth of a meter, less than what's called a micron. Pretty small, but not much smaller than that. And therefore, light microscopes cannot see, they can't see viruses, for example, just too small. The wavelength of light is too big. The virus is way below that size scale. They're oblivious to it, undetectable. To see smaller stuff, you have to use something with shorter wavelengths. Okay? So that front surface, microwave oven, is essentially a metal surface. It happens to have holes in it, but the holes are undetectable with the microwave, which is a good thing. You don't want the microwaves coming out. Because the microwaves inside that are very intense. And over the years, I've had lots of people write to me about, lots of communications about microwave ovens. Endless, really. And I have heard from people who have put their hands in microwave ovens. The modern microwave ovens have interlocks in them, so they shut off if you try to open them and try to do something bad. So it's relatively difficult to operate the microwave open in some manner, but historically you could do it, and people put their hands in it or something, and apparently it doesn't just heat your hand, which is what I thought. It actually just hurts. It's just painful immediately. It's not a heating process. Okay? Yeah, John. if you put something in that doesn't respond to waves. Food, when you start putting things other than metal in, the response is different. So metal, if you put metal things in, metal stuff reflects the microwaves because it's conducting. We'll talk more about metal, and part of the fun of this is you've all been told forever never put something metal in a microwave oven. So we'll put stuff that's metal in the microwave oven. The basic idea, it's clearly an overstatement to say never put metal in a microwave oven because the whole box is metal. So there must be some lie in this, and so we'll try to get that straight. It's definitely an overstatement. It turns out that as long as you put you don't want to put something that is a poor conductor of electricity because it will have currents flow in it and it will get hot. So a favorite terrible conductor of electricity is a twist tie. The paper or plastic strip with a thin wire in it that you use to close a bag. Bad idea. It's thin, it will get really hot. That's for one. The other thing you don't want to put in is something that's sharp, because electric charge, a sharp metal object, because electric charges are going to be driven back and forth in it by this intense electric field in the microwave. And when you push a lot of positive charge this way to the end and it hits a point, you get corona discharge or worse, right? You produce a gigantic voltage at that tip. And it's a tip, it's a sharp point. So a high voltage wire or point sends charges off on passing air molecules. It does a corona discharge. Or worse, it can actually start sending sparks. Okay, so sharp things are bad. Thin things, sharp things, actually a twist tie is both. The handle of a Chinese food container, same idea. You all have probably done this once or twice. You put something, aluminum foil typically has sharp edges, bad. It's also pretty thin. It's all iffy. So we'll do metal shortly. Before doing metal, though, I'll tell you how does the food cook. The food cooks primarily by the response of water molecules to a very intense electromagnetic wave. So when the doors close, the microwave transmitter is turned on. Bouncing around inside this box is a really intense electromagnetic wave. And so the electric field at any given location in space, it may be fluctuating all over the place, typically up and down and up and down and up and down, billions of times a second. That has effects on molecules that themselves are electrically polarized. Water is such a molecule. Any water molecule, if you go looking for water molecules, and I will flip ahead to my pictures of water molecules. Skip there. These are my pictures of a whole crew of water molecules. Water, famous H2O. It's not how are there are two hydrogens and one oxygen. How are they arranged? The two hydrogens sit sort of at tetrahedral angles on the. Thank you. I appreciate that. As I will show you here in this lovely slide. Oh yeah, now I do. Yeah, so I think of them as like Mickey Mouse's head, although that's copyrighted and all. I'll get in trouble. The oxygen is like Mickey's face, and the two ears are the hydrogens. So it's not a linear molecule. It's this funny cockeyed thing. And when that molecule assembles, the oxygen is electron hungry. It draws in the electrons from the hydrogen and leaves the hydrogen a little bit short on electron. Therefore, the hydrogen atoms are now somewhat positively charged. Hydrogen atom by itself is neutral. It's got as much positive charge as negative charge. In this situation with oxygen being greedy, the hydrogen atoms are a little short on electron density, and the Mickey's ears are somewhat positively charged. Mickey's face is somewhat negatively charged, and as a result, the molecule always has sort of a positive end and a negative end. It's actually one of the most polar molecules in nature. There are other ones that are like this. There are a lot of molecules that are completely nonpolar or essentially completely nonpolar. They do not have charged ends at all. Water does. And the result is when you put water into an electric field, it tends to line up with it, just like a compass needle tends to line up with a magnetic field. Mickey tries to line up with the electric field. Is that okay? Positive charge tries to go in the direction of the field. The negative charge tries to go opposite the direction of the field. It orients. And if you make, yeah, Toe? An object that's made of a conducting material that's very large, it will reflect the waves. So for example, if you put a heavy metal pot into the microwave oven, and you put food in, you put the lid on, the pot will reflect the microwaves. They'll never get in the food. You won't cook the food. You have simply protected, shielded the food from the microwaves. This is why if you can cook in a shallow tin, but as the pot gets thicker and thicker, it's harder and harder for the microwaves to get in the top, if you pull the top off. And so food doesn't cook all that well in a metal container. It's reasonably safe. If the metal container is heavy metal, no sharp edges, the microwaves just reflect. It's boring, and the cooking is rotten. Is that okay? Other questions? So, yeah, if you put, yeah. So the water tends to line up with the electric field. In the case of microwaves, the electric field fluctuates back and forth very fast. So the water molecules all try to line up this way, and then a fifth of a billionth of a second later, they all try to line up that way. And they go back and forth, and they experience, it's sort of a little hand-wavy to say that it's molecular friction, but it's kind of like frictional effects. If you imagine a whole lot of people packed tightly in a room, all sort of shoulder to shoulder, and I said, everybody face north, everybody face south. Face north, face south, there'd be a lot of bruised shoulders, right? You'd all be bumping into each other like crazy. That's what happens with water. It's going back and forth and back and forth, and it's getting heated by the collisions between the water molecules as they orient back and forth and back and forth. So what started as a truly electromagnetic wave becomes thermal energy. The wave gets weaker as this happens. It's basically, the water molecules end up receiving the wave, consuming its energy, and turning that into thermal energy by way of this bumping and chafing. All right? Foods that contain water, which is most foods, heat nicely in a microwave oven, as long as the water is liquid. If the water is, once the water becomes gaseous steam, it doesn't bump in it so much, so it doesn't heat as well. But also when water is ice, it doesn't work very well either, because ice is a crystalline system. The water molecules have trouble changing their orientation. They're kind of locked in place. So the microwaves want them to turn back and forth, but the water molecules in ice pretty much don't. And so they don't heat very well. And this is familiar as the problem of trying to defrost food. Or I used to think of it as the frozen burrito disaster. You all have, I don't know what the modern equivalent of the frozen burrito. Frozen burritos were terrible anyway, but we used to eat them. But you put the frozen burrito in the microwave oven and you blast it for a minute or so. And the parts that managed to thaw out gobbled up all the energy because they now have liquid water in them, which can turn back and forth and heat up more and melt and heat back. You know, certain parts got exquisitely hot. You know, top of the roof burning hot, top of the roof of your mouth burning hot, right? And other parts remained frozen and never managed to break free of that. So it was Russian roulette with every bite. You break your teeth on the ice parts and you burn your mouth on the hot parts. And you surely have some equivalent of that, right? Defrosting in the microwave is tough. What you usually do is you blast it hard for a short period of time, then turn off the oven for a while and let the hot parts, let the heat flow out of those the old-fashioned way to the cold parts and melt the ice. And you hit it again and you try to melt the ice. Hit it again, try to melt the ice. But defrosting is just not all that good. Is that okay? They also use the choice of frequency. There's nothing special about the frequency they choose. There's no special resonance in the food. There's this mythology that the food is somehow, water perhaps, sees this frequency as a magic frequency. Nope. It's just if they go to lower frequencies, the absorption of water gets weaker. And so it's harder for the microwave to heat the food. It has to pass through more times, basically, through the food before it gets it hot. So it just becomes inefficient. If they go to higher frequencies, the absorption becomes too good. And what happens is the food cooks, the surface, the water near the surface of a large piece of food absorbs so much of the microwave that there's not a lot of the microwave left in the middle of the food. And it won't cook the middle very well. So they've chosen a frequency that manages to go pretty much sort of this kind of distance into food before it gets all gobbled up by the water molecules. If they chose a higher frequency, it would only go this far in. You couldn't cook the middle of the food. If they chose a lower frequency, it would go this far in, and it's just hard to cook anything. Okay, so they're going for this sort of the sweet spot. Okay? What else? Yeah. When you change the power of the microwave, 1 through 10, what you usually do in any microwave I've ever seen is they're cycling on and off the transmitter over some number of seconds. So 10 is on all the time. 5 is on half the time. And you can actually hear it going, you hear it turning on and then off, on and off. So it's still on full blast most of the time. There may be sophisticated microwaves that actually can turn down the transmitting power. That's not my experience. Is that okay? Any other things? Oh, interference effects. Because the wave is bouncing around off all sorts of parts of the metal box, there's the possibility that one location within the food is encountering the microwave coming from 2 directions or more. One coming this way and one coming that way. And suppose the microwave is, just make it simple, coming at me from the left and from the right, and their electric fields are working. Right where I'm located, those electric fields combine to one net electric field, and I'll be the water molecule. I'll respond to the net field. If those 2 fields arrive at me so that they are in phase with one another, meaning their electric fields point up at the same time and their electric fields point down at the same time, then I'm responding to a very strong net field. Can you visualize that? This is called constructive interference. When the 2 waves, their fields add helpfully to one another. A piece of food in this location where the waves are in this arrangement cooks especially fast because it gets hit with a bigger field. The water molecules are twisted more aggressively. On the other hand, if the 2 waves coming at the same point are out of phase with one another, one of them is electric field up at the moment the other piece of field coming, the other wave's field is electric field down, they cancel, and there's like no effect here. And that means lousy cooking. And this is why microwave ovens have rotisseries and stirring systems, reflective stirrers, things to make sure that the food gets an opportunity to be at both the constructive interference points and the destructive interference, and it sort of averages out. So you want to get the uniform cooking. This is the rotisseries in the microwave ovens. Is that okay? All right. I think I've said my piece about microwave ovens, or more than it. So now what about metal things? So food cooks primarily through the water. It turns out other things also absorb microwaves to a lesser extent, and they cook. You can cook salad. You can heat salad oil, for example, in a microwave oven. It takes a while. It's not as effective. Salad oil has no water in it, or at least essentially none. What about metal? So my claim is that if you put in heavy pieces of metal, they'll simply reflect the microwaves, no big deal. As long as heavy metal, no sharp edges. What about if you put heavy sharp edges in? Well, the first, a favorite example of something not to put in a microwave oven, but this you can put in your microwave oven as long as you follow the rule. 4 seconds total. 2 seconds of warm up, 2 seconds of fun and games, and then turn it off. If you go longer, it just smells. You smell burned plastic. So It used to be that you all listened to CDs, and I could say that if you want to get rid of your roommate's CD that you're tired of listening to, you microwave it. So what this has inside it, among other things, is a very, very, very thin layer of aluminum. It is like atomically thin. It's so thin you can see through it. I don't know if you ever noticed that with CDs. You can look through them. At a bright light source, you can see through it. It's that thin. So it's barely able to reflect light, let alone reflect a microwave. And when you put it in the microwave, that aluminum layer gets hot. It absorbs microwave. Charge goes back and forth through this layer that was never meant to carry current. It heats up. And as it heats up, the plastic heats up. And plastic expands. Everything expands with heat. But plastic expands more. It tears the aluminum. Once the aluminum tears, there's sharp edges. And so what you're going to see is, and we can do it more than once, is 2 seconds of warm up at the microwave oven. The transmitter kicks on. This guy is going to spark like crazy, like the old Death Star from the original Star Wars, because it'll start heating, it'll swell the plastic, it'll tear the aluminum, and sparks will then begin to jump between the torn edges. Okay? I will prop up the CD right there at the front. You can look for it live, or now I'm going to go back to this guy. East camera. You can look live, or you can look on TV. We'll give it, I'll say 5 seconds just because I can. 1, 2, warm up. Death Star. Stop. Oh. Okay? And this one doesn't bother your microwave oven. You know, they come out nice and fresh. Yeah, it's all cooked. Once doesn't do it. Ready? 5 seconds. Ready? Warm up. 2, go. And then pop. Okay? So I mean, a reason to show you this is because it really is an electromagnetic thing in there. I have these magic lights. This is, in the old days, you actually used to repair things. And the repair person repairing your microwave oven, repairing, would bring one of these in to show it's working. This has got little neon light bulbs in it, neon bulbs, which are illuminated when charge is driven through the neon between two electric wires. Well, right now, there's no connection to this. How could you possibly have current driven back and forth through those wires? Well, it's possible in here because, clear, where's clear? Right? It really is an electric device. The charge is being driven through that neon by the electromagnetic field, electromagnetic wave. Okay? So this is like a vestigial thing. I don't know if they even sell those anymore. No one fixes microwaves. Another thing, incandescent light bulb. An incandescent light bulb, also going the way of the dodo bird, has a very thin piece of wire in it. Also, a lot of sharp edges, thin, sharp. It's a whole disaster area waiting to happen. And when we put this guy in there, charge will be driven around and things. It will light up in various ways. You can melt parts of the structure that were never supposed to have current in them or melt at all, like the support wires. So you can make the bulb like a real weird disaster. The other thing, though, is that because it has sharp edges in it, it will shoot charge out into the gas inside the bulb. Light bulbs, you might think light bulbs have no gas inside them, that they have to be in vacuum to operate. In fact, they do have gas in them. It prolonged their life. But it's not oxygen. It's gases that don't react with tungsten. So I'm going to drive charge around inside that metal, and we should get the bulb to light up. Yeah, you see the purple? You see the purple glow? Right? I'm going to stop it because it starts. We can explode the bulb. What you're seeing is the gas inside the bulb having charge shot into it, And then once it's got charge shot into it, the gas itself becomes electrically conducting, and it can absorb microwave power and light up. And that an electrically charged gas is considered another state of matter. It's not a normal gas, because normal gas molecules don't notice each other at any distance. They only notice each other when they touch. But if there's charges in them, they notice each other at a distance. In that case, it's called a plasma. And so plasma used to be a rare word, and then they made plasma television sets, and now I guess those are going away too. I want to show you plasma out in the open, though. The way we can make plasma out in the open. So what I've done to date, you can do yourself in your own microwave oven. Certainly the CDs, it's no big deal. The light bulb thing, yeah, it's no really big deal, although you can, a few seconds is good, then stop, because things get overheated and kablooey. I have actually blown up a light bulb while giving a presentation to like other faculty here. It was crazy. Okay, this is the one you do in your friend's microwave oven, because this is a scorcher. I'm going to burn a match inside the oven, and that match is going to become a piece of carbon, and carbon is a decent conductor of electricity, not all that good, and that carbon will become exquisitely hot in the microwaves, and it will heat up so hot that it will begin to put charge out into the air through a process known as thermionic emission. Just the sheer temperature and the air will become electrically charged, plasma, and the plasma will begin absorbing microwaves and will get hot, and it will rise. And normally, if you don't trap it, it rises to the top of the microwave and skittles around on the top and scorches the top of the microwave oven. I'm going to try to trap it under a beaker. So my goal is to get the match burning, trap the burning match, and hit the microwave power. Let me get everybody lined up here, guys. And if it works, plasma balls will come off the burning match and skittle around inside the beaker. Okay, there we go. All right, pile in, guys. There we go. You see the plasma ball there? So that's gas. I don't know how we can do this before it blows up the beaker. No, I don't want to have like a total disaster. Woo! All right. You can see why you don't want to do that in your microwave. All right. So I'm going to leave transformers. Oh, well, we didn't make it back to there. All right. So the test on Friday.